applied to nowadays also to biomedical signal and image processing. But my core expertise is still signal processing. Okay, so in this particular talk, we'll discuss about synthetic aperture sonar. So this is again an application area. Over time, while working on different applications areas, I've realized that uh, one may be a core signal processing or machine learning, deep learning person, but every application area has its own nuances and subtle points. So it is great if you delve deeper into the area as well, understand what sort of data is emerging out of that application, and then apply any signal processing or machine learning method on that. Okay, so we begin with the very basics. So this is sort of a tutorial kind of a thing, but I've divided the talk into two parts. The first part is about synthetic aperture sonar, where we'll start from very basics of sonar. So I'm not assuming that you know anything in this area, so we'll just start from absolutely ground zero. In the second part of the talk, I will discuss some recent papers where people have applied machine learning or deep learning, but also taking cognizance of the domain that they are applying to. So the sonar stands for sound navigation and ranging. So here we say that there is a transmitter and there is a receiver. So you can see this picture on the right. So the transmitter emits acoustic pulses. So although we call it as sound, but basically the pulses are acoustic, so it's a bigger range of frequencies than just the audible sound that humans can hear. So the transmitter emits acoustic pulses, typically ultrasound, and receiver analyzes these returning echoes, as you can see here, right? So there is an ultrasound pulse which goes into the water. So let's say this is the sea shore or the sea surface on which the ship is there. At the bottom of this ship, we have these transducers and detectors. Now the reflected wave is received and is now analyzed here. So how is the acoustic pulse reflected? Either it would strike an object, let's say a marine animal, or it would strike the bottom of the sea surface and then it would come back. So the reflected ultrasound pulse is also called an echo. Now, what is the core principle of sonar? We measure the time of flight to determine what we have to determine two things. One is the location of the object and second is the motion of the object. So key marine applications are, for example, detection and tracking of submarines, localization of underwater explosive ordnance, navigational triangulation of vessels so that you can locate these vessels, ocean floor mapping for navigation, locating schools of fish. So when multiple fishes are moving in groups, you call them as schools of fish. So locating schools of fish in modern fisheries, seabed characterization, or investigation of underwater archaeological sites. Although there can be many more marine applications than just these few ones. Now, what is the history of sonar? So, is it that humans are only have evolved this principle that you transmit pulses and then you receive the reflected wave and then locate objects? No. Some marine organisms, for example, toothed whales, including sperm whales and some dolphins, use echolocation for navigation and hunting. So they also emit waves and then the echo is received back, which they hear, and that's how they detect the objects or other marine animals in their path. So this is called as echolocation for navigation, that is to move inside the sea, or for hunting as well. Now, in 1490, Leonardo da Vinci could hear ships at a great distance through ears placed to the end of a tube immersed in water. Now, these are some initial things where people realize that they could do a lot more in the sea. Now, sinking of Titanic in 1912 would be, we can say, was one of the major events because it collided with the iceberg. So, a ship that was thought could never sink, but it ended up in the loss of too many lives. Now, this also again emphasized that there is a huge need of detecting objects in sea. If the iceberg could be detected in time through some sonars or systems like this placed on the ship, perhaps this could have been avoided. So now let's look at the kind of waves or the signals that we receive for this purpose. Acoustic waves, we can say, is a broad term for all sound waves. We can divide it into three ranges. Audible range that we humans can hear, 20 hertz to 20 kilohertz. Infrasound, that is below the sound waves, which is below 20 hertz. And ultrasound, above this 20 audible range, it is about 20 kilohertz. Primarily, sonar uses ultrasound, that is frequencies above 20 kilohertz. And there is an advantage why we use these waves, because while audible sound can travel much further in water, but ultrasound provides superior resolution, reduced interference, and more accurate Doppler measurement. So this makes ultrasound the preferred choice for underwater applications. Now, there are two major types of sonar that we talk about. One is the passive sonar and another is the active sonar. So passive sonar means that you're not transmitting any pulse, but you're only hearing. So here the ship is only hearing, the devices on the ship are only hearing. So maybe there is a submarine underneath and its moving mechanism or its engines, etc., are producing noise, say radiation noise, that is being heard by this receiving sonar system. So it's a passive sonar, but still maybe would be able to make out whether there are objects in the sea nearby. Active sonar, on the other hand, would transmit a pulse, and those pulses will then be reflected back, and the echo would be heard, and that's how they do the navigation purpose. Now, let's look at the concept of an antenna array, which is a useful thing in this particular domain. So, let us say that there is a target here and its waves are emitted and received by an antenna array here. So let's say this is what is placed on your ship. And so there is one antenna here, there is another. So in general, there is a planar antenna array that is utilized in this domain. But let's say there are two antennas like this. So the wave has traveled a distance of r0 to come to this position, whereas it has traveled a distance of r1 to come to this position. So what you would be hearing is at these antennas, you receive a signal at time, let's say t naught, and here you receive it at t naught plus delta tau. So of course, this range is longer, so that means it will take a longer time to come here. And let's say the velocity of the wave, acoustic wave, is c. So that means this delta r, additional distance traveled, is nothing but delta tau into c. So we know what is this delta r. Now, if we know this delta r, we can also look at this geometry. Delta x is the distance between two successive antenna elements. So that means that we can figure out what is this theta. So delta r is delta x into cos theta. Since we know delta x, we have computed delta r because we know delta tau. So that means that theta is equal to cos inverse of delta r by delta x. So this implies that if we place more than one antenna, we can figure out from which direction or along which direction the target is located. So in addition, if you are also using an active sonar, so that means you transmit a pulse, you receive a signal back. So the time traveled distance you can measure, so that means you know the distance, uh, and you also know the angle at which it is located, so that means you can localize the object clearly into the sea. If we visualize this sonar setup, so let's say this is the sea bed, that is bottom of the sea, and this is the sea surface, and this is the depth from the sea surface to the sea bottom. And if we look at, so let's say the sonar transducer and receivers are here, so we say that if you look at this angle, this is called as the squint angle. So if squint angle is 90 degrees, so that means sonar is looking in this direction. If it is 0 degree, that means it is looking vertically downward or along along your along your side, right? So we talk about two types of range resolution. There is one range resolution and there is one azimuth resolution. So if you're moving along this direction and there are two animals located here, then the minimum distance between two animals that you can resolve along this direction is called as the azimuth resolution, and along this direction is called as a range resolution. So for example, these are two marine animals. So how, what is the minimum distance that they should be apart that you're able to resolve through your sonar setup? That is called as the range resolution. I hope these concepts are clear. If there is any question, I am happy to take it now and then I'll move forward. So I cannot see the chat history. So someone needs to read it out for me if there is a question in the chat. Okay, hoping that there is no question here. So now we also, so if you look at the conventional sonar, this is how it looks like. So you have a transducer here and see the, so this is the region in which if any submarine is located inside it, would be actually detected. But let's say the submarine is actually moving to this spot and it is not being covered by the transmitted signal by this ship. We call this also as the shadow zone. So that means that if there is a submarine and it's an enemy submarine, may like to hide in the shadow zone of your sonar and would not be detected. So what is the way out? Then you talk about a variable depth sonar. So what is a variable depth sonar? That this time there is an attachment here and with which your sonar system is located. So it will move up and down. And now the range that is being covered is this as well as this. And hence now it would be way easier for you to detect the sonar. The submarine or the enemy's ship. Now, there are different types of active sonar. Synthetic aperture sonar is one where you are sort of moving alongside, but at the same time, you have you have an array of your transmitters which are projecting signals down here. So your range is very large, and since it is also moving, so you cover a wider range of the area. And that's why it is called as a synthetic aperture sonar, because in a way you're saying that synthetically you are expanding the aperture of the sonar. And then there is a multi-beam sonar where maybe there is a single beam, but from multiple sources you are putting the beam, so it becomes a multi-beam sonar. Again, this also increases the range that you can cover. Sector scan sonar, there is only one beam here, but it keeps rotating like this so that you can again cover a wider range. So there is a steering transducer which would move the element or your antenna so that you can cover the wider range. Then there is side scan sonar that you're scanning to the side, whereas there can be a forward scan sonar where the transducer is placed at the front end or the nose of the ship so that you can range in the forward direction. So maybe let's say this is an iceberg or there is a wave there. So you're moving, you're looking forward in the forward direction and slightly in the shallow water or just in the upper layers of the water as well as on the front side of the ship. Now this is a comparison table showing difference between various sonar imaging systems. So side scan sonar or SSS and SAS are basically two very popular kind of scenarios. So I have tabulated this looking at the operating frequency, the resolution, effective imaging range, and the kind of interference rejection that they are capable of. So if we look at the synthetic aperture sonar, its resolution is very high. Centimeter scale resolution is there. Effective imaging range is also very good, around 300 meters to 3 kilometers, and interference rejection is very strong. So whether it is synthetic aperture sonar or synthetic aperture radar, so sort of there are lots of similarities that you can see in the basic principles of the two. This is one example image where people had imaged using SAS system, and they got this image showing that there is a debris there at the bottom of the sea. When this ship was recovered, so indeed it looked like whatever was the SAS image which was taken for this. Common active sonar technologies, as I already said, they are two, SSS, that is the side scan sonar, and synthetic aperture sonar. So SSS or side scan sonar is well established, widely used. However, it has certain limitations. For example, resolution is limited by the physical size of the transducer array. Azimuth resolution of side scan sonar also degrades with range. Now, this becomes a bigger limitation of the side scan sonar. Now, synthetic aperture sonar aims to overcome these limitations by synthesizing a larger aperture. So now signals from different positions are coherently combined because there is an array of antennas and emulates a much larger physical array leading to a higher resolution. Particularly improves azimuth resolution, which is along the direction of travel, as well as is independent of range, which we saw was a limitation of the side scan sonar. So there are a number of publicly available SAS datasets that you can utilize for your research. So for example, you look at this dataset, it is complex value. So basically the data when you capture the images, they become complex valued after you do all baseband processing, etc. So, so this is one domain where if you look at this data which is complex valued, you can talk about complex neural networks, you can apply those principles, or you can actually look at different type of signal processing applied to these images. So, for example, this SASET dataset was released in 2018, is a big dataset, and these are they are capturing seafloor textures, and they have also annotated it. For example, sand, mud, seagrass, rock, etc. So key features are 129 high resolution sonar snippets with hand segmented masks are there, and the use cases or the application where you can use it is the, for example, image segmentation as well as classification, because the textures are marked there. Now, Kraken is another data set which is for multi-label underwater object classification. Again, here 86 SAS images and 82 optical images with corresponding labels are provided to you. Underwater object categories are, for example, cylinders, metamines, natural objects, etc. Then two more data sets are here, so you can, the links are given here also, the papers are here. You can download these data sets and you can get started with your research that you have been studying in this summer school as well. We also talk about look characteristics in sonar imaging. Look refers to distinct illumination and recording of the target area. So for example, we can talk about single look imaging and multiple look imaging. So as we said, in single side scan sonar, you are actually throwing the beam only once, so that's why it is called side scan sonar. So images formed from data acquired during a single pass of the sonar sensor. Each point on the target is illuminated and recorded only once from a specific aspect. Analogous is to taking a single photograph of a scene. Resolution in the along track direction is limited by the physical transducer size. In the multiple look imaging, for example, SAS, you are actually scanning each position multiple times. So if I go back to this figure, you can see that this ship is also moving. And for example, if I look at these particular pixels on the seashore, they have been captured when the ship was here. They are also being captured when the ship is here. So as it is moving along this direction, there are many points which are captured multiple times in synthetic aperture sonar. This actually helps you in improving the resolution and the signal to noise ratio of the collected image. So you have image generated by combining data from multiple passes. Each point on the target is illuminated and recorded multiple times from varying viewpoints, similar to capturing a scene from several angles and integrating that information. So in SAS, these multiple looks are coherently combined. Now, this is also important that you do coherent combination of these to synthesize a larger aperture, leading to high along track resolution. So benefits of multiple look imaging, of course, it would help you reduce speckle noise, improve target detection and classification, etc. So it's not that only SAS can have multiple looks, you can also achieve it with SSS. How? By multiple passes, running several passes over the same area, or maybe multi-beam SSS, that you can actually put multiple transducers and then capture imaging from them. So then also it becomes multi-beam. Key distinction, SAS requires multiple looks, whereas SSS is typically single look but can be enhanced with multi-look techniques. Now, what are the transmitted pulse used in synthetic aperture sonar? So we generally say it's a chirp signal or a linear frequency modulated signal, LFM, like this. So you can clearly see here that frequency is initially low and then is increasing over time. So LFM chirp signals frequency changes linearly over time. So if we write this signal mathematically, this is how you would write it. So it is actually for a predefined duration. So TP is the duration of the duration for which this LFM chirp or the pulse is transmitted. So that is why you have a rectangular signal, rep T by TP. A is the max amplitude, that is, it is not from 1 to -1, but from A to -A, if A is used here. Here in this diagram, A is equal to 1. And then you have e raised to the power j, 2 by f naught t is the center frequency, and then the frequency is increasing beyond this. So you can say f0 is the start frequency plus pi alpha t square. So this is how the frequency is increasing linearly with time. So f0 is the start frequency of the chirp and alpha is the chirp rate. And chirp rate is nothing but bandwidth divided by TP. So this rectangular envelope provides a simplified model for understanding the basic principles. But in SAS, actually, you are not transmitting just a pure cosine wave or a cosine pulse of limited duration, but actually you transmit a chirp signal, and we'll see mathematically why from signal point of view, signal processing point of view, it makes sense. So there are practical considerations, and we consider it under the concept of pulse shaping. The idealized rectangular pulse envelope has limitations in practical SAS system. Why? We know that a rectangular pulse will have many spectral side lobes if we take the Fourier transform of that signal. So this leads to potential interference and range side lobes after pulse compression. Right, so there are many spectral side lobes that lead to potential interference. So we need to control that. Then we also need to have so there is a bandwidth abrupt transition. So if rectangular pulse has abrupt, brick wall kind of transitions on both sides, that would result in a broad frequency spectrum, and you need to also control that because you don't have infinite bandwidth. So to mitigate these issues, the transmitted pulse is often shaped using windowing function. So this comes under pulse shaping, that instead of pure rectangular pulse, as I have shown you, is the sort of for ease of understanding the concept. But in actual practice, you won't be using a rectangular pulse, but you will be using the windowing functions. For example, Hamming, Hanning, Blackman, Harris, Gaussian windows, etc. I hope you guys have studied about these concepts in DSP, how the windowing actually controls the power that is leaking into the side lobes and controls the bandwidth of the whole thing. The equation for the transmitted signal would then incorporate the chosen window function instead of the rectangular function. Now, what is the role of the LFM or the Chuck pulse? So let's look at that also. In traditional sonar, there is a trade-off between two things. One is the pulse duration. Longer the pulse duration implies that you have transmitted more energy, right? So which implies that you would improve on the detection of echoes that you're receiving back, because you're transmitting those pulses into the sea and then they are being reflected back. A lot of energy would be dissipated. So if you push in more energy, then you still have chances that you will hear back the echoes. Now, so that means that you would like a pulse duration to be longer so that you can pump in more power. Now, range resolution, however, the shorter duration implies that you will be able to detect closely spaced targets. So if the duration of your pulse is longer, so that means that you would be compromising on the range resolution, like what is the minimal close separation that you can distinguish, right? So there is a trade-off between pulse duration and the range resolution. Now, LFM or the Chuck pulse helps you overcome this trade-off. How? A longer duration Chuck pulse is now transmitted, injecting a significant amount of energy into the water. At the same time, because of this linearly frequency modulated pulse, we'll see that it actually leads to pulse compression, and we'll understand this concept in the coming slides. Thus, the chirp enables high energy transmission without sacrificing the potential for high resolution. So let's look at it mathematically. That let's say you transmitted a rectangular, ideal scenario, rectangular LFM pulse into the sea, and you receive a reflected signal back. Now, your point target was at a range R, located at a range R, so that's why your signal would be delayed. What would be the amount of delay? It will be because it will go and come back, so it is traversing a distance of 2r, and c is the velocity of the acoustic wave that you have transmitted. So that means tau is equal to 2r by c. So after this much delay, let's say you receive the signal back, and because of some slight attenuation or whatever has happened, Your received signal's amplitude is no longer A but is actually the B. So B is the complex amplitude scaling factor, tau is the two-way travel time of the acoustic wave, C is the speed of sound or the acoustic waves that you have considered in that particular medium, typically water or wherever in the sea. Basically the uh, the profiling of the sea water is also done, or the sea area wherever you want to use your sonar system. Generally, you also do the profiling of that place as well. Now, as we earlier discussed that it actually uses coherent crossing of received pulses. So how would it happen? So match filtering or cross correlation between the received signal and the transmitted signal. So received signal is RT, and because it is a complex signal, so you're doing S star T minus tau. This is your transmitted signal after a delay that you want to do the coherent crossing, so you know tau, so you will do this. This is the cross correlation you will do, and then you will analyze this white or signal, right? So match filtering helps you maximize signal to noise ratio, and will also see that because of this LFM pulse, once you do this cross correlation, we'll see that the long term actually compresses, improving range resolution. So typical, let's look at some example SAS parameters so that we can understand the system. So we discussed that there is a start frequency in the LFM chart, 2 pi f naught t plus alpha pi alpha t square. So f naught was the start frequency, or we can also say is the center frequency. So typically few kilohertz to several hundred kilohertz. Let's say, for example, to understand, we consider 100 kilohertz. So choice depends on the desired balance between range, lower frequencies, and resolution, higher frequencies. Bandwidth, often a fraction of the center frequency, for example, 10 to 50% of your center frequency. So if it was 100 kilohertz, and let's say we consider it as 20% of that would be 20 kilohertz, right? Key to range resolution. The bandwidth is the primary factor determining the achievable range resolution after pulse compression. So this is again a very important factor that we can see. So now what we have seen here, what is our center frequency, what is 100 kilohertz, what is our bandwidth of the chirp, actually 20 kilohertz. So that means it starts from 100 kilohertz and the end frequency will be 120 kilohertz. So that's what we are saying here. Now pulse duration is TP. Typically it is few milliseconds to tens of milliseconds. Let's consider an example of 10 milliseconds. So longer duration, as we had already discussed, increases the transmitted energy. So we are considering TP to be 10 milliseconds now. That's long the chirp pulse would last. Chirp rate, now what would be the chirp rate? We have already decided that frequency will go from 100 to 120 kilohertz. So we have decided. So now we can compute what should be the rate at which the frequency should increase, so that in 10 milliseconds it starts from 100 kilohertz to 120 kilohertz. So then which will be this rate will be the chirp rate. So chirp rate is nothing now. We can understand bandwidth, which is 20 kilohertz divided by TP. 10 millisecond is equal to 0.01 second. So that means alpha is equal to 2 megahertz per second. So this is the rate at which linearly the frequency should increase. Every second it should increase by 2 megahertz. So that means in 10 millisecond it will increase by 20 kilohertz. Intuitive explanation, the chirp rate represents the speed at which the frequency of the transmitted pulse changes over time in hertz per second. A higher chirp rate means frequency changes more rapidly over the pulse duration, often resulting in larger bandwidth. Delay to echo or delta T is related to the range or R to the target. And how it is related? If target is located at a distance R, then it is delta T is equal to 2R by C. For example, for a target located at 75 meters from the sea surface, it implies that delta t will be equal to 0.1 second. So that means after 100 millisecond, you will receive the echo back. So chirp signal bandwidth alpha we have already seen 2 megahertz per second. Pulse duration we had already decided 10 millisecond. Bandwidth we had already decided 20 kilohertz and can also be written as alpha is equal to bandwidth by TP or bandwidth is equal to alpha into TP. Whichever way, if you want to fix alpha and TP, then you know what is the bandwidth it would be covering. So chirp signal's frequency changes by 2 megahertz per second. Since our pulses last for 0.01 second, the total frequency change is 0.01 into 2 megahertz is equal to 20 kilohertz. I am again and again doing this calculation so that you can understand this concept clearly. So if the chirp started at F0, it will end at F0 plus 20 kilohertz. You could also have a negative chirp rate. If the chirp rate was negative, you can say that I am starting from F0 but ending at F0 minus 20 kilohertz. So key takeaway is chirp rate and pulse duration determine the total bandwidth of the chirp signal. Now this is important that you have one is chirp rate and another is your pulse duration. They together determine what is the total bandwidth of your chirp signal. And this becomes important when we do talk about the pulse compression, as we'll see. Now, what is the significance of this chirp signal? So, let us say that you initially transmitted this orange colored pulse and there is a noise over the channel. So, what you receive is this blue thing, which is the noisy signal that you're receiving. Yeah. Now you don't know whether there is this contains echoes which are received from the after striking the targets. But actually, if it was noiseless scenario and we would have received 1, 2, 3, 4, 5 echoes, so that means there were 5 targets in different locations from which the echo was received, right? Now, how would you detect them? You will say that at the receiver, I am receiving this blue signal. Now, I'll do coherent processing. Will actually use like reflect our transmitted pulse or do the cross correlation of the two, right? Do that. So, match filter output will look at that. And now match filter output would be something like this because this pulse and this is, let's say, rectangular pulse again correlated with the rectangular pulse will give you a triangular pulse. So this is how you're getting. So this has the highest amplitude because the target was nearer, the targets were going farther away. That's why you can see that after the match filter output also decreases in amplitude as the target is away. But here, you're still able to locate that at 5 seconds, there is one target at 5 seconds, another at 7, 9, 11, 13, and so on. Now, let's say that the targets were further closer to each other. You will see that the matched filter output will start smudging into each other. And that is when we say that the range resolution starts decreasing because you're not able to resolve precisely where your targets are located. Whereas, so here we use the rectangular pulse. Whereas, if we had used a chirp signal like this, see it is a rectangular pulse. So here also these are rectangular but pure cosinusoid inside them. So rectangular but pure cosinusoid inside them. Here it is rectangular but a chirp signal inside. So now this time there is a chirp. You can see frequency is linearly increasing. Here the frequency is constant. So now this time you receive these pulses, but the received signal is again noisy signal blue color and you have to detect this yellow part. If you do the cross correlation now of these LFM chirp received signal, this signal, received signal, and do the cross correlation with the transmitted LFM pulse, you will see this, the match filter output to be something like this. So you can see that here, if it is a pure cosinusoid versus a chirp signal, you can see here the cross correlation output is smushed and it's difficult to determine where the targets are located, but here they are so clear, and the compression actually of the match filter output has happened. So each of the pulse has actually become compressed and you can precisely locate where they are, how it is happening. So duration of the compressed pulse is, we call it as TC, which is actually inversely proportional to the bandwidth of the channel. So this is where it has actually made an impact. So earlier, if it was pure cosinusoidal signal, so there is no bandwidth, it's in the frequency domain, a single impulse located at that frequency. But now, since we have a linearly frequency modulated signal that we transmitted, so it has a finite bandwidth, and that bandwidth we have seen is equal to 20 kilohertz. So if it was 20 kilohertz in our example, then TC is 1 upon 20 kilohertz is equal to roughly 50 seconds. Now range resolution or delta R improved is what? So means that initially what was the range without this pulse compression concept, delta R was equal to TP was the rectangular pulse duration, C into TP by 2 is equal to 7.5 meters. But this time it is actually determined by TC, which is much larger than your TP, right? TP was only 0.01 second, whereas TC is equal to 50 seconds. So if you look at this, C into TC by 2, if you do, then this time you are getting a range resolution of 3.75 centimeters. So earlier you could resolve two targets, minimum separation between them should be 7.5 meters for you to resolve. But now, if the two targets are separated by 3.75 centimeters, this much smaller distance, then also you can resolve and see that they are two distinct targets. So you can see that huge range resolution has happened. Why? Because of the difference in this TC and TP. TC is the duration of the compressed pulse. You also, so this significant improvement from the resolution of a, but remember that the duration for which this LFM pulse is transmitted, it's still equal to TP. But the compressed pulse is actually, TC is related to the, inversely related to the bandwidth of this chirp signal. So that's what is bringing the improvement. Processing gain is approximately the ratio of the pulse duration to the compressed pulse duration, and you can see that it is TP upon TC is roughly equal to 200. So that's the processing gain that we. This gain in signal to noise ratio is also key benefit of using the chirp and pulse compression. But now why this pulse compression is happening? I just said that TC will now determine what will be your range resolution, but how? So let's look at this. Say you had transmitted a pure cosinusoidal signal per TP duration. So if we look at this signal, it is actually a multiplication of rectangular pulse with a pure cosinusoid. Pure cosinusoid has frequency spectrum like this. There is one impulse at minus f0, another at f0. And the rectangular pulse would have a spectrum in the frequency domain, which will be a sinc function. So which will have the first nulls would be located at 1 by Tp and minus 1 by Tp, where Tp is the duration of this. I hope this you understand from basic course of signals and system. Now, since it is multiplication in the time domain of the cosinusoid and rectangular pulse, so it is convolution in the frequency domain. Once you convolve this, so this sinc will get located at minus f0 and another sinc you will see at f0. What would be the bandwidth of the sinc? It is actually going from f0 to this Taylor point is f0 plus 1 by Tp, and this point is f0 minus 1 by t, right? So you can see that the total bandwidth is 2 by t. Now look at what if we had sent LFM pulse. Again, because there is a rectangular shape or pulse with which you have multiplied this chunk. So that means that for the rectangular pulse, we still have, because it has Tp as a duration. So minus 1 by Tp and 1 by Tp are the first nulls of the two. But this time for the LFM chirp, it starts from F0 and the end frequency is F0 plus BW bandwidth, which is 20 kilohertz in our example. So that means this is the spectrum of the LFM chirp. Now when you do the convolution, you see this in the frequency domain, it has spread it compared to the previous one. Previously it was F0 to F0 plus 1 by Tp. This time it is F0, which is in the center, to F0 plus bandwidth plus 1 by Tp. Now this BW is 1 upon Tc is what we are considering this BW to be equal to. So you can see that in the frequency domain, it has, the spectrum has become wider. Now that means in the time domain, the pulse would actually get compressed. And this 1 by Tc will start now dominating because this BW is way higher than 1 upon Tp. Right? That leads to your pulse compression. So the result of this match filtering of the received echo with the transmitted signal leads to pulse compression of the chirp signal. It effectively shortens the duration of the received pulse after match filtering while increasing its peak amplitude, which had also increased if you look at this diagram. See how much peaking has happened, right? Very sharp peak, so you can precisely locate where your targets were, right? And now this results in compressed pulse with a duration comparable to that of a short, unmodulated pulse, providing high range resolution. We saw that range resolution improved from 7.5 meters to 3.75 centimeters for our example, right? By combining the transmission of a long duration chirp pulse with the subsequent pulse compression of the echo, SAS achieves both high energy for better detection range and performance in noisy environment and high range resolution for detailed imaging of underwater structures and objects. So example SAS parameters, for example, are these. Center frequency F0 is the operating frequency. We said that bandwidth we considered, remember we said that it could be 10 to 15% of your center frequency. We have taken 20% of center frequency. Pulse duration we considered 10 millisecond, which is also the chirp duration. Chirp rate alpha was 2 megahertz per second for our case. And that is nothing but equal to bandwidth by Tp. Speed of sound we considered 1500 millimeter per second into the sea water. Range resolution, it is 3.75 centimeter, and how we have calculated C into Tc by 2 or C divided by 2 into bandwidth. Processing gain is Tp into bandwidth, around 200 for our case. Why signals are complex valued? For you to think, because you need to do baseband conversion, and that's where you get actually complex valued signals. So I'll now start with some of the recent works on SAS using MLDM. So before this, I would like to take a pause for about 3-4 minutes. If there is any question, I would like to take that. But this is a slight break for 5 minutes. Yes. Anyone having any questions? Doesn't seem to have any question at all. How many participants are there? We have around 13 attendees as of now. Can they unmute themselves? I don't think so.
No.
Yeah.
Ma'am, we cannot unmute the participant, ma'am.
Okay, so that means they need to write in the chat window.
Yes, ma'am, yes.
Okay. So if anyone has any question, I would be happy to take. After 2 minutes, 2-3 minutes, I'll start with the second work. Okay, let's begin. So now in this part of the talk, I'll be discussing some recent works on SAS using machine learning and deep learning. So what are the problem statements for us to solve using signal processing, machine learning or deep learning? One application is segmentation and classification of objects. For example, marine animals, trash, shipwreck, UXOs, that is unexploded ordnance which are there under sea, seabed terrain classification. So, for example, you know that Titanic shipwreck was detected very late, right? So that means that even identification or detection of these is also an important work or the application. We would also like to innovate methods or apply methods for image enhancement because generally the images captured using these technologies would be noisy because the sea is very turbulent. At some places, it may be very, very turbulent. There are animals moving into the sea. So, a lot of clutter is there. They are also making noise. So, lots of things are there, movements are there. So we do see that the signal is noisy, has lot of clutter. There would be multiple reflections within the sea. For example, the pulse that you are transmitting, it may reflect multiple times from the sea surface as well as sea bottom, may reflect from various animals. So that's why the data is very noisy. You can apply super resolution to improve the quality of the images, as we have already discussed that range resolution or maybe your azimuth resolution is somehow limited. So you can also improve them. Autofocusing is another problem. Maybe you want to have unmanned vehicles on which you are putting this kind of a system which is now moving over the sea surface and collecting images. You would like autofocusing sort of a setup there. Motion correction, animals are also moving, your signal is going in, you will see some Doppler effects and would like to do the motion correction. Moreover, your system might also be having jitters or the motion because it is the the system is also moving, right? So you may like to have motion correction. Then the data is almost always limited. So that means that, and if we use technologies like DL, they are data hungry. So that means that another application domain is that you would like to use generative AI or do synthetic data generation so that you can build reliable systems. Then you would also like to transmit or have smaller systems or transmitted small amount of data. So that means that you would also like to employ compressive sensing based reconstruction. So these are all typical signal and image processing problems, whether you solve them using traditional signal processing or you solve them using machine learning or deep learning is completely up to you. From DL point of view or machine learning point of view, there are certain challenges, but at the same time, they offer opportunities. For example, data sets are generally highly imbalanced compared to so many domains. I would say these data sets are hugely imbalanced. For example, let's say that you have deployed a system which can identify marine animals, different marine animals can detect and identify them, but suddenly at some place, let's say a deep sea animal came up in the upper layers of the sea. In that case, your system had never seen that kind of an animal. So suddenly there is a new animal that has come up. So in the DL domain, we call it as out of domain object detection kind of a problem. Now, similarly, maybe you are capturing images, but most of the time you're capturing images of the seabed, and there are only few images where your marine animals are there or objects of interest are there. So again, if your larger interest is in animal classification, then again it will become hugely imbalanced data set. Then there is a scarcity of labeled data. We can say it can also be said as lot of unlabeled data is there, because labeling implies, let's say you want to do seashore classification or detection of animal. So the images are noisy and someone needs to be there who is an expert who can figure out that in these regions, this is where an animal is there, this is where it is not. So generally the data is feeble. Even on the spectrogram, you see very feeble points where you need to identify that maybe here there are marine animals. So data is largely unannotated, unlabeled data or weakly labeled. Maybe there is a lot of error that has been done. So we can say that or only few labels have been put up by some people. So that means that there is a weakly labeled data. Scarcity of data itself. Small amount of data compared to your natural images, you collect huge amount of data. People keep uploading images of them, and so that's why you have huge amount of data. But when it comes to only SAS data, there is a scarcity. So training DL models is a bit of a problem. But at the same time, you can use transfer learning sort of a scenario. If the data is weakly labeled, these days we talk about semi-supervised learning. We can employ uh, these sorts of newer architectures of semi-supervised learning, which take a small amount of labeled data and a large amount of unlabeled data, but put it in the supervised training framework, and you can learn from there. If data imbalance is there, maybe you can use generative model, you can do class balancing, augmentation, but it should be domain specific augmentation that you should do. Then there is noise also impacts heavily noisy data. So that means that now you have another opportunity to improve upon the models, which can actually detect from very noisy data, or you can also do super resolution of the images that you have captured. The signal is complex, which adds another challenge. You shouldn't be, we know that when it comes to images, a large amount of information is in the phase signal. So it shouldn't be that you only use magnitude of images and not the phase images. They also carry a lot of useful information. So another opportunity area is that one can use complex neural networks, which are which are also there in the literature. Then mostly domain knowledge integration doesn't happen in the DL model. People just apply DL model arbitrarily. So if you want to build meaningful DL models which are also explainable, then maybe you can use the domain knowledge and also test on the explainability. For example, these days we have models like GradCam++, which put the visual saliency on what areas or what has been seen in the, which area has been seen in the image based on which the model is saying that it belongs to this class. So you can also build those explainable model. Now there are lots of other explainable models have come into the literature. Then lack of generalizability to the new environment. So if you have built up a model which is on, let's say, the Indian Ocean, and you start deploying it on some other side of the ocean, say in the Pacific Ocean or some other places, you may see that it's a new environment, so the data is slightly different and there may be a lack of generalizability of the model. So now let's look at some of the literature papers. I have collated some papers and I'm discussing with you. So for example, look at this reference by Chen et al., which is on the deep convolutional neural networks. Uh, so here, the task that they have considered is SAS image segmentation, and challenges: the limited labeled SAS data is available for supervised training. High image resolution increases computational cost. Clutter and noise obscure target detection. Variability in seabed environments affects model generalization. So these are the challenges also identified in this paper. This is one of the recent papers in 2024. So what are the novelties or contributions made by the authors? They have built a fully convolutional ladder network for segmentation along with classification. They used GradCam for visual interpretability of CNN predictions, and then also use semi-supervised learning to improve segmentation with fewer labeled samples, as we had been discussing. So the method, for example, looks like you have, so as we said that there is a fully convolutional ladder network. So you have at this end, you have encoder, so you can see input comes over here. These are different con layers. And then this is where it is going for the segmentation, and this is where it is coming for the reconstruction. So if you look at, for example, UNet kind of an architecture, this would be UNet kind of an architecture, which is very famous for segmentation. But at the same time, with the similar architecture, you're also doing reconstruction. So now you get two losses. One loss is a reconstruction loss, and another is a segmentation loss. So if your encoder is learning good amount of features or good embedding are coming here, it would help in segmentation as well as reconstruction. So this reconstruction loss would then start guiding your segmentation, because if reconstruction is happening, so that means it will also be able to identify the objects, and hence the segmentation would also be good. So these two losses are used in tandem or together by making one loss function, and that loss is propagated back, and this is how the network is trained. So the network is jointly trained on image level classification, reconstruction, and segmentation, because class labels you're extracting here, you can put a small layers here and then do the classification, here reconstruction, here segmentation. All the three losses are together used for training the network. So these are some of the results. So you can see this is the SAS image, and now you see it is how difficult it is to identify where the objects are located in this. This is manual segmentation. So those experts are really fewer who can really identify where the objects are in this image, and those are the manual labels. But some manual labels may have some errors also. That's why we say that, or weakly labeled, some objects might not be labeled by the manual annotator. So that's why we say at times the data is weakly labeled. And then once we do this, whatever segmentation we have done, when we fuse it over this SAS, original SAS image, see, now we can clearly see where the objects are. And if we look at the heat map, which is the visual saliency or GradCam, it can also say that what it has seen, based on which it is identifying the objects. So you can see that they have really done a good job. Now, this is another paper published in 2025 itself, this year. And this is on enhancing physical spatial resolution of synthetic aperture sonar images based on convolutional neural network. Again, CNNs have been used here. So the task was to enhance SAS image resolution. Again, the challenge is limited aperture restricts spatial resolution that we have been discussing in this talk frequently. SAS images suffer from noise and multipath effects because the signal would be reflected from the surface and the bottom of the sea repeatedly from different objects, and then all those multiple paths would be received by you. So it's noisy because of turbulence and so many radiation noise of different objects or other noises, and has multi-part effects. Maintaining target integrity while enhancing resolution is a bigger challenge. So what is the novelty or contribution in this work? They propose unit like CNN for SAS resolution enhancement. Trained model refines targets to theoretical impulse responses. Improvement in both single and multiple target cases. So which is what they have shown in their work. So now let's see what the method looks like. So you have both low resolution and high resolution images. So you go from, so these are your DL layers. So you're downsampling in this direction, upsampling in this direction. And if you look at each block, this is how each block looks like. There are 2D con layers followed by batch normalization plus redo activation. So you have two such blocks. And then you have max pool down there. So it reduces the size. That's why we are saying downsampling in this direction. And you have upsampling in this direction, which we call as a transpose convolution, upsampling with this. And so if your input image is this, you want to reach here, which is the high resolution image. So this path is what you train. So you have some data which is low resolution as well as high resolution. You train such that finally every low resolution it learns to create a high resolution out of that. So let's look at the results. So the predicted high resolution imaging, A is the predicted high resolution imaging, whereas B is the ground truth high resolution imaging. See how good is the prediction. And C is the input low resolution. So basically to the model you gave this, after the model has been trained, you predict these as the high resolution images, 3 targets are located, and you see this was the ground truth. So indeed we are reaching there. Now here multiple targets are there. Now the predicted impulse function of multiple targets. So this time here you're converting images to high resolution, and here you're predicting the impulse function of the target. So that means from the image now you will detect where the impulse is located. So predicted impulse response of the multiple targets is here. So this is the input, which was the predicted one. You give now as input. This is your ground truth of the impulse function, and this is what you get as the output. This is another work which was published in 2022 by Sun et al. And here they did SAS image segmentation. The challenge is limited pixel level labeled SAS data for training, high texture variability in seabed environments, noise and weak signals in SAS images, computational constraints for real-time processing, because you would like to deploy those systems on the ship or on your unmanned vehicles. So novelty or contribution, they proposed an iterative, deep, unsupervised segmentation. So basically building a unsupervised segmentation methodology so that you don't bother about the labels at all, integrating deep learning with superpixel clustering. Introduced iterative, then improving upon them because there was a limited label data as well. and converted that to deep semi-supervised segmentation to enhance learning with partial labels, and they could achieve SOTA performance while reducing computational cost per inference. So now let's look at the architecture. This is the input image. First, they put a unit kind of an architecture. So already pre-trained unit you can have. And then whatever are the outputs coming out of unit segmentation network, they are using superpixel algorithm on top of that, right? And then they make some superpixels and you store those superpixels in the memory. Then what they do is that they do the k-means clustering of these superpixels, and then they update these superpixel labels in the memory. So similar superpixels they will combine and do the updation of this memory. And then, so they will now, so whatever were the superpixels here, they will now start clubbing those superpixels based on this k-means clustering, and they will update the superpixel labels, and then they will give the pseudo pixel labels. To every pixel, they will give a label, class label. So different superpixels or whatever has come, they will give class labels, and then they will consider a loss between whatever segmentation was coming out from UNet, whatever is coming out of this path, they build a loss between them and then update the network. So basically at the end of the whole process, UNet should get learned and should start giving you objects at the out of this. And then whatever is a trained unit, you can employ that for the inference part. So here the idea is that you're using superpixel algorithm, using k-means clustering to combine those superpixels to form objects, and you're saying at the end of the whole, and the two losses you're combining together or taking a difference somehow, you're using the uh, the the two losses that you're sort of utilizing together, the difference between them, contrastive loss you will build between the two outputs, and then you will train this unit, and in the end you will say that at the end of this, the whatever k-means clustering is doing and plugging together some superpixels and saying that this is one object, the same information will come out of this, where this unit will actually get stabilized. So they in their data, the data they considered had 7 classes. So if we look at the labeled versus unlabeled pixel, 53.4% were labeled, 46.6% were unlabeled pixels. If you look at the classes, there were 7 classes, and you can see that there is imbalance in the data. For example, shadow class is only 0.00, so that means only 0.3% is present of this shadow data. Then there is dark sand, bright sand, and so on. So they did both segmentation as well as classification. And see, these are the segmentation maps of C-band textures from semi-labeled data, right? So you can see that class color mapping, SH implies, which is the SH is this class, shadow is shadow and dark sand. If we see DS is green, this is dark sand, blue is shadow, sand, and so on. And they could do very reliable segmentation. And they used also semi-supervised learning. So unsupervised results are in D, whereas semi-supervised are in E. And you can see that the quality has improved actually from D to E, because now it is actually giving more precise results because of a limited amount of label data, which is also present in the semi-supervised learning. This is another task that researchers have done. This is on auto-focusing on SAS images. Now, this time, this is the problem that is solved. The challenges are systematic phase errors cause structural distortion in SAS images. Existing autofocus methods require manual tuning and iterative optimization, whereas real-time deployment on unmanned underwater vehicles is constrained by computational limits. So, novelty or contribution introduces deep adaptive phase learning, a CNN-based autofocus model leveraging SAS-specific case space information, corrects quadratic phase errors, sinusoidal and sawtooth errors in a single pass, achieves superior autofocus performance compared to phase gradient autofocus and metric-based methods without manual training. So what is the method? Let's look at their methodology, DAPL. So you can see here, this is a ground truth image. So the task is that they want to do autofocusing, improved focusing, right? So this is your ground truth image. If you take consider these, we have already discussed that the data is complex valued. So there is a real part of the image and the imaginary part. And let's say you put a defocusing model and this is what you are receiving in fact as a collected image, right? Now you will have different images here. DRC, you employ this block here and a phase module. So this is dynamic range detection module. So you, not range, but processing on this real part of the image and the imaginary part, or the phase, the magnitude part and the phase part, and you get these two images out of this. Now they employ a architecture which is pre-trained dense net. First they connect that, and then they have a regression network. And the regression network gives some outputs that they do some remove mean and then do the detrending. And the output of that is nothing but the estimated phase, right? So if you want to do phase correction in a SAS image, so that means you need to estimate by which phase the error is there. And then you need to put a phase correction module. So these are pre-trained architectures that you would like to fine tune. How would you do that? They consider this data also, take its FFT. And now they use these two to do the phase error correction in the frequency domain. That's why they're saying phase correction in k-space. And then whatever is the corrected image, use IFFT, then again a DRC module, and then you have the auto-focused, well-focused DRC image. So basically this is the module that you need to train. Now, how the phase correction is happening, you have a defocused image, you take its Fourier, defocused image, take its Fourier, you obtain GE, which is here, magnitude and phase. You are estimating phase error. So phi cap, which is here, phase, aperture phase correction that you would like to employ. You add this phase to this, and then you have this autofocused image. So basically, your loss would be between this ground truth and the autofocused image. This loss would be minimum, and this loss would be gradients of this loss would be back propagated to train, fine tune what? Fine tune this, so that this model learns to predict the phase with which the correction has to happen. So that's how this whole model is being trained. And finally, the good part of this method was that it was using both real and imaginary images and is doing, finally when model gets trained, it automatically focuses the images. So, or does the phase error correction. So these are some of the results. You can see that DEPL is supervised, and they did with semi-supervised, supervised methods. And this showing that image quality improvement for each image of the test set compared to ground truth is what we see in this figure. For all plots, higher numbers indicate better performance. Box extend from the first quartile to third. So here this is a PSNR change, this is MSSSIM change, and this is SSIM change. And as we can see that DAPL has the boxes to more of the right, so it is able to maintain better quality or give better quality after applying for phase error correction. This is another work on SAS image autofocusing. It introduces progressive diffusion autofocus for iterative SAS image refinement compared to the previous model. Use a diffusion inspired model. So these days diffusion models are very, very famous. So this uses a diffusion inspired model to reverse phase corruption progressively. So now let's look at this model. So this time you have this block applied repeatedly, and individual this block looks like this. Again, it's the same thing. Dense net, the same type of a network, but is being applied repeatedly. So while training, you will actually, while training, you actually feed the defocused image and you should get a auto focused image at the end of this path. At each stage, you're putting a loss function and you're tuning this architecture back to keep improving. While training, you will have the ground truth so that you can tune these blocks randomly, and then you can have the complete architecture. So these are the results of different methodologies. This is the ground truth. This is a defocused image. You can see, for example, if you look at this place, see this image is different. Here there is a change in the image. So you have different changes in the images. So here in this image, see, this part is in the defocused image has completely gone, whereas this is sharper. And here also see this part, it is completely gone here, here it is sharper. So DAPL, for example, this is PGA progressive. DAPL was the previous method. PGA progressive diffusion autofocus method is PDA is that method, and you can see that it's really able to do good job. At least here you can see it is able to do good job, and here also it is able to detect with clarity. It's not there in the autofocus, so it is able to show with clarity. This is another work published last year, Classify Underwater Acoustic Targets. And again, the problems remain almost similar, limited data, noisy data, etc., etc. So novelty or contribution, this time they evaluated through PAN on the evaluation of PAN, that is existing networks on the deep dataset, demonstrate ImageNet models outperform pre-trained audio models. PANs are the pre-trained audio models. They in passive sonar tasks. So let's see this. So overall framework is something like this. You receive a signal, you do data pre-processing. So audio waveform is transformed into logarithmic Mel frequency spectrogram. Then you do data augmentation. So data augmentation is by spectrogram augmentation and mix-up are added during training to improve model robustness. And then you have data analysis, so sort of a ImageNet pre-trained architecture they used, and then they did the classification. So these are the PANS model, which are the existing audio models, pre-trained audio models, and they saw that accuracy, classification accuracy, if they, so the models are CNN, this, Wavegram, MobileNet, V1, ResNet, and these, and the number of parameters is also here listed here. See, the best performance that we receive here is around 70.6%, and the number of parameters are 79.7 million parameters. Whereas when they're using TIM, that is ImageNet trained medical, ImageNet trained models, they're using TIM models, and see this time the best accuracy is obtained on this model, 70.6 to 73.7. So a rise of around 3% accuracy, and the number of parameters has gone very small 27.9 million compared to 79.7. So that means the model is smaller, more reliable, and inference time will also be impacted with a smaller model. So similarly, SAS image segmentation is tried in another model like this, where their novelty is propose a deep multi-look sequence network for SAS segmentation, introduce a temporal spatial fusion mechanism. I really like this paper so because in a way they try to fuse the domain knowledge into this. So what they're doing is, this is a depiction of the difference between true angle of arrival with that of approximation made in the K space. So you have frequency, so Kx, which is directly proportional to frequency, and Ky, which is directly proportional to angle of arrival, right? So the picture overlays colored isolines. So these are the isolines of true angle of arrivals. So these are the isolines for angle of arrivals. 0 degree, 1, minus 1.5 degrees, and so on, right? And frequency vertical lines into K space. The gray colored grid that you see, rectangular grid, attached to the axis show the angle of arrival and frequency approximations used in their architecture, which they are calling as MNSP-NET. So what they do is the following. So this is, for example, image with no filtering. So they are dividing into smaller bands. So this is a filter. So it is only passing this uh, amount of data or this band of the data. This is passing this band. So these are different bands that they are having multiple filters. So once they're filtering this raw image with this, these are the kind of images that they're receiving. So in a way, they are sort of saying that it is like a multi-look sort of a scenario, that I am looking at the scene from a filter or which is only scanning this much area. And what is this? If you go back, vertical axis is doing the denoting the angle. So in a way, they are saying we are considering all frequencies, but looking at only these band of angles. Then you're increasing the you're you're sort of shifting the angles, and now you're looking at this band. Then you're looking at this band of angles. So in a way, as if you're rotating your receiver and scanning different angular regions of the image, uh, different angular regions in the domain or where you're scanning the scene, and then you have these multi-look images. They combine these multi-look images. They so you have real, you have the real and imaginary part of the image. Take the Fourier, and now these are those multi-look filters, and then whatever are the outputs, you take uh, inverse Fourier, then you have the DRC module, downsampler unit, squeeze and excitation network, and finally in the LSTM you take the embedding out. And here also you're doing some unit crossing, concatenating, and then doing the final segmentation. So this they call the architecture as MLSP, multi-look sequence path, and then process these images and obtain very good results. So they really got very good results compared to the existing SOTA methods. They really got improved performance on different classes, and that's where I would like to stop here. I would like to thank all researchers, academicians, and practitioners whose resource materials were handy for us in preparing this tutorial. So two of my UG interns in my lab, they really helped me put up these slides. So I would like to also thank them for their contribution. Thank you. I would like to take questions if any. Yes. Are there any questions? So Hemant, can we stop now?
Hello, ma'am.
Yeah.
Actually, ma'am, Hemant sir is not there at the moment.
Okay, so can we stop now because I have finished with my presentation? Because I don't think anyone has any question here too.
Okay, ma'am. Can I talk to Hemant sir? Then I.
Yeah, yeah.
Sir. Yes, ma'am. You can stop. But ma'am, you can write email ID in chat box if anybody has queries related to this PPT.
Okay.
Okay, ma'am. Okay.
Okay, thank you so much. I hope participants enjoyed the talk and I would like to log out here. Thank you.
Okay. Thank you.
To all the participants, see, if you have any question, you may again email to the madam or you can email to me. So how was the session today? Please respond in the chat box. Did you find it something interesting? It was basically sonar, deep learning in the sonar applications. Anand?
Yes, sir.
Am I audible? No?
Yes, sir. Audible.
Yes, yes. So see, these are basically another different aspect, and in the afternoon you will have the another session. It is basically by the faculty of the IIT Bhubaneswar, Dr. Himanshu Padole. He will give you the basically again insights in the biosignal processing with the Alzheimer oriented applications. Again using the GSP. There you also you would find it bit interesting. Because in signal processing, its fundamentals are same, but the applications, even when you apply at the different applications, it is not obvious to apply those things. So that way, that lecture would be helpful to understand you the further basics. Okay, so if you don't have any questions, so please join at 3. And tomorrow also, one speaker is basically from IIT Indore, Dr. Vivek Kanhangar. He will again brief you about the interesting applications of the image processing. So, thank you all. And please try to attempt the quiz by today. We have already extended the timeline so that the quiz is actually mandatory for giving the certificates. So even you can attempt it multiple times if you are finding problem, but it must be attempted, right? So okay. So and tomorrow in the afternoon session, we will basically have the some we will have the just discussion where you will also be allowed. We will have the live interact. We can interact as per the academy's policy. All can participate. Whatever experience is there. So it is basically 1 hour, 1-to-1 interaction. Whatever suggestions are there, and certificates will be distributed there only. Okay, I leave it. Thank you.